Integration by substitution. So when we look at finding antiderivatives of functions, we have to remember that some of the functions that we took derivatives of were very complicated. So one example is the chain rule. We started with a composite function, and when we took the derivative of that function, we had to use the chain rule, and we had to take the derivative of the outside function times the derivative of the inside function. And we had to do this by substituting in a z in order to substitute in for the inside function so we could find all the pieces that we need. So that means that if we're finding the antiderivative of something of the form f prime of g of x times g prime of x, that we are undoing the chain rule. So how do I identify that I need to use this method, that my derivative came from the chain rule, and what are the pieces necessary to get back to the original function, also known as the antiderivative? So we're going to start with an example where we're going to take the derivative of a function using the chain rule. From there, we'll take the result and look at how to go backwards so that we'll know the answer before we even begin. So the example we're going to look at is going to be e to the x squared. So remember from the chain rule, if we take the derivative of e to the x squared, the inside function, or the function that got plugged in, was x squared. And then the derivative of that was 2x. So when we did the chain rule, we rewrote our y as e to the z, and our dy dz was e to the z. So then when we multiplied our two derivatives together and plugged back in for z, we found that the derivative of e to the x squared was 2x times e to the x squared. In general, if we have an e function, we get the same thing back, and we multiply by the derivative of the power. So the idea here is that if we now integrate 2x e to the x squared, we need to get back to e to the x squared plus c. That's our goal. We just need to figure out how to go backwards from here to here. So let's take a look at the process and how this works and figure out why it works. And this method, when we undo the chain rule, is called integration by substitution. So what we need to do when we do integration by substitution is we need to look at the original function and we need to try to determine if it was the result of a chain rule. And that's not always easy. That's something that comes with doing a lot of these problems and a lot of practice. But here, when I have an e function, I look to see if it's sort of the main function in the problem and not just part of a bigger function. So here it is. And what I need to do is I need to look at the power of e and determine if the derivative of that power is also present in my antiderivative. So here, my power is x squared, and the derivative of x squared is 2x. Since both those pieces are here, I know this is a good candidate for integration by substitution. So now, what does the process look like? Well, for substitution, if our e is our main function, if you have e to something complicated, then you're going to let u equal the power of e. So here, my e was raised to the x squared, so my u is going to be x squared. Now, once I have my u, I need to find du dx, the derivative of u with respect to x. So when I take the derivative of x squared, I get 2x. So this is the next part. This is similar to what we were doing when we did the chain rule with our z. Only now there's an extra step. Now I need to solve for du. So here I'm going to multiply my dx up to get du equals 2x dx. And we need to talk about why we do that and what that means. So our goal here is to find an antiderivative in terms of u that is equivalent to the antiderivative that we're trying to take that's in terms of x. Because the way it's written right now, we can't use our basics table to find the antiderivative. So in order to turn everything into u, we need a way to replace our operator, dx, which tells us what the variable is, with a du. Because we won't be able to take the antiderivative unless everything is in terms of u and has a du at the end. So we have to figure out what the equivalent is. Well, because these our ratios, we can actually multiply that up to figure out how that ratio works. So my du is equivalent to 2x dx. Now, these are the beginning steps for all of our substitution problems. We're going to figure out what our u is. That's the hardest part. Then we take the derivative and then we solve for du. That part we do on the side, and those derivatives should be relatively basic, so that part shouldn't be hard. Now, we go back to our original antiderivative and we substitute in based on our u and our du. So notice here that I'm going to switch the order of my 2x and e to the x squared. These things are multiplied together, so the order doesn't matter. 3 times 4 is the same as 4 times 3. The reason I switch the order is just so you can see how I substituted in the du. So instead of x squared in the power, I'm going to write in my u, and then instead of 2x dx, I'm going to substitute in du. So my integral becomes e to the u du once I make my substitution. And again, the reason I want to be able to do this is because now this antiderivative is one from my chart. We know the antiderivative of e to the x dx, which means we know the antiderivative of e to the u du. So the antiderivative of e to the u is just e to the u. It doesn't change. So from this step right here to this step right here, I found the antiderivative. And this is important because once you find the antiderivative, your integral symbol and your du, they disappear because they were operators. They were telling me what to do. They said, find the antiderivative of e to the u with respect to u. So once I've done that, those two symbols are gone. Just like when you do 3 plus 4 equals 7, you don't ask where the plus went because the plus is something you do. That's the same thing here. So again, the integral says find the antiderivative of, and then you have your function e to the u, and then du says with respect to u. So that tells you the variable. So the integral and the du disappear, and I have e to the u plus c. Now, just like when I did the chain rule, I don't want my final answer to have anything but x's in it. So I need to substitute back in what u represented. So remember, u represented x squared. So my final step is to plug x squared back in for u. So my final answer is that my antiderivative is e to the x squared plus c. And I know, because I started with that, that that's what I wanted my answer to be. So my process looks like this. And so again, the difficult parts are first recognizing that you need to do u substitution. Again, that's something that comes with a lot of practice. So the more problems you do, the better you will get at recognizing that you have to do u substitution. The next tricky part is identifying what your u is. Once you have your u, then you need to find your du, and that's not usually too bad because that's just a basic derivative. And then it's substituting in carefully, right? So once everything is substituted in, you should have an antiderivative that you can use the basics chart for. So in order to do this, what we were doing is we were finding the original inside function. And that can be tricky because we don't even know what the original composite function was. We know the derivative of the original composite function. So we have to take a look at it and do our best to try to figure out what the original inside function was, and that's your u. So remember, we did the chain rule for 4 types of functions. So we had the power rule, so we had some sort of parentheses raised to a power. We had exponentials, that's the type we just did. We had natural logs of complicated things, and we have trigonometric functions. So that means we have 4 types that we need to make sure we know how to undo with integration by substitution. So we're going to start by looking at exponential functions. We're going to look at how we can undo various exponential functions using this method, and we'll use the example we just did as a basic map or guideline of how we're going to do these. So let's take a look. With exponential functions, you want your main function in the problem to be of the form e to some function f of x. What you want to do is you want to first look at that power of e. You might need to isolate it on the side if you can't do this visually, and determine if the derivative of the power is also present in the problem. If it is, then your function is a good candidate for substitution. Example 1. The antiderivative of cosine x e to the sine x dx. So remember, we want to first check out the power of e. So here the power of e is sine x. I've done this on the side just to make sure I can see why I'm doing substitution. So if my power is sine x, I also want the derivative of that to be part of my problem. So the derivative of sine is cosine, and cosine is also part of my problem. So I know that this is a good candidate for substitution. So I'm going to go ahead by using the method of integration by substitution to try to solve this problem. So if I think back to the last problem, I know that one of my first steps here is to figure out what my u is. So again, if you have e to something complicated, your u is going to be the power of e. So here, that means that my u is sine x. So now that I have my u, I need to take the derivative. So du dx, the derivative of sine, is cosine. And so my du is going to be cosine x dx. So I'm multiplying up the dx. So these are the two pieces that I need, my u and my du, in order to do my substitution. This du dx is sort of a middle step just to get over to du. So now when I set up my integral, I'm going to start by substituting in what u equals. So u was the power of e. That's my first step. Just get that part out of the way. Then I need to look at what's left. So here, I'm left with a cosine x dx. So I want to go over to my du, and I want to compare what I have for a du to what I have left in my integral. Hopefully, it's an exact match. If it's an exact match, I can just write in du, which I can here. If it's not an exact match, then there's two possibilities. The first possibility is that it's only off by a constant. If your du only differs by a constant from what's in your function, you can keep going. You can always manipulate things by a constant. However, if the function is different, then that means maybe you weren't supposed to use substitution and you were supposed to use some other method. So this is one of the places where we can figure out if we've done the wrong process. So if you try to plug in your du, but your function is different than the function remaining, then maybe you need to try something else. Fortunately, here they were the same. So I have the integral of e to the u du. So at this point is when I take the antiderivative. So after this equal sign, I will no longer have my integral symbol or du because I will have found the antiderivative. The antiderivative of e to the u is e to the u. So again, I don't want u in my final answer. Instead, I want to substitute back in what u represented. So I have e to the sine x plus c. So again, this is the antiderivative. So it answers the question, what function has a derivative of cosine e to the sine x? And my answer, e to the sine x plus c. If I were to take the derivative, I should get back the function I started with up at the top. So let's look at another example. Example 2. X plus 1 times e to the x squared plus 2x dx. So I want you to notice that you have parentheses in this problem because later we're going to look at parentheses to a power problems, and we have an e to something complicated. We need to figure out what the main function is here. I want you to notice that this parenthesis is not raised to a power. It's just x plus 1. And e is raised to something complicated. So my main function here is the e function. So here I have e to the x squared plus 2x. And I remember that when I pick my u, I want my u to be the power of e. So that means that for this problem, I'm going to pick my u to be x squared plus 2x. Now, from here, I need to take the derivative of that function. So the derivative of x squared is 2x, and the derivative of 2x is 2. So my du is 2x plus 2 dx. So again, in this step, I'm just multiplying up the dx. So now I have a u and I have a du. So now I start my process of substitution. So I start by plugging in the power of u instead of x squared plus 2x. Then I want to evaluate what's left. So what's left here is an x plus 1 dx. So I come over to my du, and I see that I have a 2x plus 2 dx. So that's slightly different. So now I need to determine, am I different by a function, like an x, or am I just different by a constant? Because if I'm only different by a constant, I can finish my problem. So what I notice here is that if I factor out a 2, I get du equals 2 times x plus 1 dx, which means that I'm only different by a factor of 2, and that's a constant. So what I need to do is I need to divide both sides by 2. So I get 1/2 du equals x plus 1 dx. My goal here is to get what's on the right to match exactly what was left in my function. So in order to get x plus 1 dx, I needed to have 1/2 du. So when I substitute in for x plus 1 dx, I'm going to substitute in 1/2 du. Now, our constant multiple rule said that if you have a constant, it's going to multiply the derivative of your function. I like to pull my constants in front. So I'm going to put the 1/2 in front, and I'm going to do this in 2 steps just so you can see. So this means that my constant 1/2 is going to multiply the antiderivative of e to the u du. Well, the antiderivative of e to the u is e to the u. I don't want my final answer to have a u in it. So instead, I'm going to substitute back in what u represented, which was x squared plus 2x. And so now I have my final answer. And we have this extra 1/2 in front because, again, we needed it for our du in order to make our substitution. We were able to pull it out front, and using the constant multiple rule, it carried through to our antiderivative. So what was interesting about this example was, again, that when we had our du, we had to do a little algebraic manipulation to get everything in the right form to finish the problem. So that happens occasionally, I'd say about 50% of the time, so we want to get comfortable with getting du into the right form. Let's look at another example. Example 3. We have 7x cubed times x to the 4th. So here again, we want to look and we want to see if the power of e is related to the other function. We know the derivative of x to the 4th is 4x cubed. I see an x cubed out front, so I'm feeling pretty good that this is a substitution problem. So I start off by, again, picking my u, and for e problems, my u is going to be the power of e, which is x to the 4th. So that means my du is the derivative of that, 4x cubed. And for my final du, I have 4x cubed dx. So now I come back to my original function and I start my substitution process. So u gets plugged in for the power of e, and then I look at what's left. What's left is 7x cubed dx. I don't have a 7x cubed, I have a 4x cubed. So in order to get 7x cubed, I need to multiply both sides by 7/4 du. So again, that's just some basic algebra manipulation. So if I multiply by 7/4, the 4's are going to cancel, and that'll give me my 7x cubed dx. So 7/4 du equals 7x cubed dx. So that means I'm going to substitute in a 7/4 du. Again, I need everything to be in terms of u in order to successfully finish my integration by substitution problem. If there are any x's left at all, I won't be able to do this. So I'm going to pull my 7/4 out to the front. Again, you don't have to pull it to the front. That's just a matter of preference. So my constant multiple rule says that my 7/4 is going to multiply the antiderivative of e to the u. Antiderivative of e to the u is e to the u, but I don't want a u in my final answer. So I have 7/4 e to the x to the 4th plus c. So I've substituted back in for u to get my final answer. And again, I will remind you that from this step to this step, is where I actually took the antiderivative. That's why my integral and my dx have disappeared, because I've successfully found the antiderivative using my antiderivative chart. Let's look at one more that uses an exponential function that's not in terms of e. Example 4. The antiderivative of 9 times 6 to the 3t dt. So this is in exponential form, but it doesn't actually use the e function. 90% of the time, the exponential integration by substitution problems you do will involve the e. But you can also do it with other exponential functions, so I wanted to make sure that you've seen one of these. The map is pretty much the same. So here, we have 6 raised to the 3t. So our u is still going to substitute in for the power, but now it's the power of 6. So 6 is raised to the 3t, so my u is 3t. My du dt, my derivative of 3t, is 3. So du is 3 dt. So here, when I start to do my u substitution, again, I begin by substituting in my u. I look at what's left. So what's left here is a 9 dt. I look at my du, and my du is 3 dt. So that's only different by a constant. So that means I can multiply both sides by 3 to get the constant that I need to finish my substitution. So you can multiply or divide out any constants you need. So now, instead of 9 dt, I'm going to have 3 du. So 3 du. Again, I'm going to pull my constant out front. My constant's a 3. And I have 6 to the u du. So since I'm using my constant multiple rule, my 3 will multiply my answer. And from my basics chart for antiderivatives, I know that the antiderivative of 6 to the u is 6 to the u divided by the natural log of 6. With antiderivatives, we divide by the natural log of the base. But again, I don't want a u in my final answer, so I need to substitute back in. So I have 3 times 6 to the 3t divided by the natural log of 6 plus c. So this was a good problem because it had some manipulation of du. It wasn't exactly the e problem, but we had to be careful with our constants, and we may have had to actually go back and refer to the chart if you didn't remember the antiderivative of a to the x. But here we were able to successfully complete it using integration by substitution. So those are the examples of exponentials.